you. My name is Stadnichuk. Today I will talk about terrestrial gamma-ray flashes produced by complex thunderstorm electric structures. Terrestrial gamma-ray flashes are very short and very bright sources of gamma radiation produced by thunderstorms. And today there are two classes of models that describe terrestrial gamma-ray flashes. The first class of models predicts that gamma-ray flashes are the product of electrons accelerated in the close vicinity of lightning leaders. And the second class of models predicts gamma-ray flashes as the product of relativistic runaway electron avalanches. In my presentation, I will talk about the second class of models. So, in relativistic feedback discharge model, terrestrial gamma-ray flashes are predicted as a product of relativistic runaway electron avalanches amplified by the relativistic feedback. The relativistic feedback is the process of multiplication of relativistic runaway electron avalanches by so-called relativistic feedback by positrons and backscattered gamma rays. And this feedback is characterized by feedback factor, and if this feedback factor is more than 1, then relativistic runaway electron avalanches become self-sustainable, and number of relativistic particles within the thunderstorm rapidly increases. So, analytically, a relativistic feedback discharge model can be described with feedback operator. This feedback operator includes all the physics relevant to relativistic feedback, and it shows how the distribution of relativistic runaway electron avalanches changes in one cycle of feedback. And feedback factor can be found as an eigenvalue of this feedback operator. The feedback factor being equal to 1 is a necessary condition for terrestrial gamma-ray flash production. So we can plot these conditions, and from this plot we see that the electric fields that were observed experimentally directly within the thunderstorm do not reach the values required for self-sustainable relativistic feedback discharge model. But relativistic feedback discharge model assumes the dynamics of relativistic runaway electron avalanches within uniform electric field. But recently, it was shown that in complex thunderstorm electric structures, an additional feedback mechanism called reactive feedback appears. The reactive feedback can be described in the following way. Imagine a thunderstorm with heterogeneous electric field geometry, which consists of several separate electric regions which can accelerate relativistic runaway electron avalanches. In such structure, if a gamma-ray photon propagates through the structure, then at some point it can interact with air molecules within a region and produce relativistic runaway electron avalanche. This relativistic runaway electron avalanche will radiate bremsstrahlung gamma rays. So here we see the process of gamma ray multiplication. So it interacts with electric field regions, and in the result, gamma ray multiplies. And if new gamma rays further propagate through this thunderstorm with complex structure and interact with other regions, they also can multiply. And if this process loops, then we also get self-sustainable relativistic runaway electron avalanches physics. And this is the essence of reactive feedback, because if we have the high-energy particle exchange between separate thunderstorm regions, then relativistic runaway electron avalanches can become self-sustainable and possibly produce a TGF. Runaway electron dynamics within such complex thunderstorm electric structure can be described with feedback operator matrix, which consists of matrix elements which describe how different regions act on each other. For example, the separate regions amplify each other by reactive feedback, and also regions can act on themselves by relativistic feedback. So this operator includes all the physics relevant to relativistic runaway electron avalanches multiplication processes. And feedback factor can be found as the eigenvalue of this operator. In this way, we can plot the conditions necessary for terrestrial gamma-ray flashes for different electric field geometries. And here we see the following trend. So on this line, at the right, the conditions necessary for positron feedback are plotted. And here we see that the most strong electric field is required for self-sustainable relativistic runaway electron avalanches development. And for the most complex multi-cell reactor model with the most complex geometry, the electric field required for terrestrial gamma-ray flashes is the lowest. So here we see the following thing, that the more complex electric field structure within the thunderstorm is, the lower electric field is required for self-sustainable relativistic runaway electron avalanches development, which can produce possibly terrestrial gamma-ray flashes also. So, in conclusions, I would like to say that in this presentation I showed that heterogeneous geometry of electric field can lead to additional feedback mechanism in runaway electrons physics, which is called reactive feedback. And reactive feedback arises due to high energy particles exchange between separate thunderstorm regions. The dynamics of runaway electrons with reactive feedback can be described by feedback operator, and feedback factor can be found as eigenvalue of this operator. And the most important conclusion is that the more complex electric structure of the thunderstorm is, then the easier it is to produce TGF by relativistic runaway electron avalanches. Thank you for your attention.
Thank you. We thank the speaker.